Okay, I am going to explain Coulombs Law. So Coulombs Law is a law for the force that charged particles exert on each other. Sorry. So if I have charge 1 and charge 2, we know that, for instance, if the charges are of the same type, that there will be a repulsive force between them, which tries to repel them away from each other. This force will act along the line connecting the two charges, and the forces they exert on each other will be equal and opposite. In my notation, when I write subscripts on a force, like right here, I am using active voice. So you should read this as the force that 2 exerts on 1. Okay? So you can think of the first subscript being the subject, and you can look at the second subject as being the object. That's at least in terms of grammar and language. In some of the videos I've uploaded, you'll find that most people have the opposite preference, that they prefer to use the opposite notation, where they think of this as the force received by 1 from 2. I really don't like that because it's difficult to remember, and usually when it comes to education, using the active voice almost always yields greater benefits because it involves less use of short-term memory. And your short-term memory is taxed enough as it is in physics. A relevant variable for describing this force is in terms of the distance between the two charges. So I'm going to represent that distance by r12. So r12 is the distance between charge 1 and charge 2. And there are basically 3 rules for this force. It is directly proportional to the product of the charges, and it is inversely proportional to the square of the distance between them. So the product of the charges is Q1 times Q2. The distance squared between the charges is R12 squared, and I need to do a proportionality. So the force is directly proportional to the product of the charges. So that means the force that 1 exerts on 2 is going to be proportional. So there's a constant of proportionality out here. It's directly proportional to the product of the charges. So that means it's equal to some constant times those charges. And it's inversely proportional to the square of the distance between them, so I divide by the distance squared. That's where the inverse comes in. And finally, I'm talking about a force magnitude here. So I should put an absolute value bar around the product of the charges because they could be positive or negative depending on the circumstances. The proportionality constant is called Coulomb's constant. And Coulomb's constant has a special form. It is equal to 1 over 4 pi epsilon 0, where epsilon 0 is something called the permittivity of free space. Epsilon 0 is 8.85 times 10 to the negative 12th, and Coulomb's constant is 8.99 times 10 to the 9th. The units for Coulomb's constant are Newton meters squared per Coulomb squared, and the units for the permittivity of free space are the reciprocal of those units, Coulomb squared per Newton meter squared. So usually we like to write this constant of proportionality in terms of the permittivity of free space because it's just more useful later on in the course. So I'm going to go ahead and do that. It's really a matter of personal preference which one you use. As far as I'm concerned, whenever we run into this particular ratio, though, we're just going to replace it with this number for Coulomb's constant. I'm going to do a couple of examples with the force. The first example is just to compute the magnitude of the force between two charges. So let's say we have charge 1 is 3 microcoulombs and charge 2 is 4 microcoulombs. Then what is the magnitude of the force of repulsion that charge 1 exerts on charge 2? Okay, so that's basically what the question is. And by the way, it's worth pointing out, how do you think the size of this vector compares to the size of that one? So this is the force that 2 exerts on 1. And this is the force that 1 exerts on 2. How do those compare in magnitude? Do you guys know? They're equal, right? Newton's third law. This is an action-reaction pair. So Newton's third law says that if an object exerts a force on another object, then the other object exerts a force back on it, which is equal in magnitude but opposite in direction. So Newton's third law is kind of built in here in terms of how we're drawing these forces. Okay, so to start this problem, I'm going to make a list of knowns, unknowns, and equations. The relevant equation is obviously the magnitude equation for the force between two charges, and that's just Coulombs law. You should probably go ahead and memorize Coulombs law because it's not going away. It's going to be coming up over and over again throughout the course. My unknown is the distance. Well, actually, oops, I should have specified that. So the distance between these charges, let's say, is 12 centimeters. Okay. My unknown is the magnitude of the force. I have an equation to get it, but I don't actually have it. And my knowns are the two charges and R12. Charge 1 is 3 microcoulombs. Charge 2 is 4 microcoulombs. And the distance is 12 centimeters. So all I have to do now is compute that force using the equation. So the magnitude of the force that 1 exerts on 2 is 1 over 4 pi epsilon 0. Absolute value of the product of Q1 times Q2 divided by R12 squared. That's equal to 8.99 times 10 to the ninth Newton meter squared per Coulomb squared times the absolute value. And let me remind myself what the values are. 3, 4, and 12. So 3 microcoulombs, 4 microcoulombs, and 12 centimeters squared. And I'd better get in touch with what these magnitudes are. So micro stands for 10 to the negative 6, right? So micro is 10 to the negative 6. Oops. Nano is 10 to the negative 9. Centi, 10 to the negative 2. Kilo, 10 to the 3. Milli, 10 to the negative 3. Right, these are SI prefixes. That's not a complete list, but you should know them. Okay, so micro is 10 to the negative 6. And once again, that's something helpful to remember. If you memorize it, you don't have to look it up, and that saves a lot of time. So here we go. 10 to the negative 6, 10 to the negative 6, and 10 to the negative 2. The absolute value bars are around something that's positive, so I can ignore them. So when I do this arithmetic, I'm going to have 8.99 times 10 to the 9 times 10 to the negative 6 times 10 to the negative 6 times 3 times 4 all over 144 times 10 to the negative 4. The 10 to the negative 4 comes from the 10 to the negative 2 squared. And as far as units, there's going to be the units from Coulomb's constant. There's going to be units from the product of the two charges, and there's going to be units from the distance squared. This will cancel this, and that will cancel that. So I'm left with newtons as my units, as expected. Now I got to do 8.99 times 3 times 4 over 144. So first of all, 3 times 4 is 12, and 144 is 12 squared. So what I can do is I can cancel this with that and just make that into a 12. So now I have 8.99 over 12 times 10 to the negative 3 upstairs and 10 to the negative 4 downstairs. Okay. I'm going to go ahead and round my 8.99 to a 9. So I'm going to say 8.99 over 12. It's approximately 9 over 12, which is 9 over 3 times 4, which makes this 3/4. So that's 0.75. So now I have approximately 0.75 times 10 to the first power newtons, or 7.5 newtons. And that is the answer. Next, we'll do an example on determining the direction of the force. So for example 2, I'm going to have 3 charges. Q1, Q2, and Q3. And I want to know which of these best describes the net force acting on Q3. So the net force acting on Q3 it could point up, it could point to the left, down, or to the right. And the idea is, well, which of those is it? So the point of interest is Q3. And I want to know, okay, how's that going to work out? Now I'm going to assume that all of these have the same amount of charge. But Q2 is going to be negative, and Q3 is going to be positive. Okay. So Q1 is positive, Q2 is negative, and Q3 is positive. Furthermore, this is going to be an equilateral triangle. So that means all the side lengths are the same. And this is a 60, 60, 60 triangle. Okay. So we have two forces acting on Q3. And the first thing to take note of is that the magnitude of the force that acts on Q3 is going to be K, Q3, Q1 or 2. I'll just put Q1 for now, over A squared, absolute value. That's just going to work out to be K, Q squared over A squared, right? And that's going to be the case whether I use the positive charge or the negative charge to act on Q3, because Q1 and Q2 both have the same magnitude of charge. So this is the same as the force that 2 exerts on 3. So I'm going to have the same magnitude for the force. Also, the forces are going to be parallel to these lines. In the case of Q2 acting on Q3, the force is going to point down into the right because it's an attractive force, right? A positive charge and a negative charge will have an attractive force. And the force that Q1 exerts on Q3 will point up into the right due to the fact that it is a repulsive force. Okay. Now, The only thing I really need now is some angles, so I have some idea of what the directionality is. From the way it's drawn, you can almost kind of tell how things are going to work out. But what I'm going to do is I'm going to go ahead and draw a horizontal line here. And this is just an imaginary line. And it's helpful to draw a horizontal line because that is parallel to the base of this triangle. When you have parallel lines in a figure, you can start to figure out some angles. So I know is that this horizontal line, when it's cut by the slanted line, makes an angle of 60 degrees. So this is 60 degrees. And furthermore, I know that when this horizontal line is cut the other way, by this guy, that this is 60 degrees. And so this guy is also 60 degrees. So if I draw those forces in a free body diagram for 3, they will both make an angle of 60 degrees with the x-axis. So here's the force that 1 exerts on 3. Here's the force that 2 exerts on 3. This is 60 degrees, and that's 60 degrees. So if I want the net force, I'd better express these in terms of components and work from there. I'm going to go and represent the 60 degrees by an angle theta. And it's the same angle for both forces. So now let's go ahead and make a force chart. So I have force in the x direction, force in the y direction. And I have the force that 1 exerts on 3 and the force that 2 exerts on 3. I know that the force that 1 exerts on 3 is going to have a positive x component and a positive y component because it points to the right and upwards. I know that the force that 2 exerts on 3 is going to have a positive x component and a negative y component because it points to the right and downwards. Oops. Okay. Then as far as what those components are, well, in general, to get the x component of a vector, it is going to be plus or minus the magnitude of that vector times either sine of theta or cosine of theta. And whether it's sine of theta or cosine of theta depends on whether that component is opposite to or adjacent to the angle of interest. So for instance, if I'm looking at f(1,3), let me change the color here. This would be the x component, and this would be the y component. So this would be fx and fy. And you can see that the x component, the horizontal piece, is adjacent to this angle of 60 degrees, whereas the y component is opposite to that angle. So for the x component, I would use cosine of theta, because cosine of theta is adjacent over hypotenuse. And for the y component, I would use sine of theta, because the sine of theta is opposite over hypotenuse. So my force is the magnitude f(1,3) times the cosine of theta, magnitude of f(1,3) times the sine of theta, magnitude of f(2,3) times the cosine of theta, the magnitude of f(2,3) times the sine of theta. It's okay if it takes you a second to see why I chose what I did, but regardless, you do have to practice this and make sure that you really know how to do it. This is a skill set from Physics 1, and your teacher should have drilled this into you when you were learning about forces. And if they didn't, something we have to work on together throughout the semester. Okay, so we have our force chart, And to compute the net force, we need to compute the sum of the forces. To compute the sum of the forces, you just add components by components and then combine them using basic properties of vectors like magnitude formula and the formula for angles. So I drew two y components. Okay, so the x component of the net force is going to be F13 cosine theta plus F23 cosine theta. And the y component of the net force is F13 sine theta minus F23 sine theta. But remember that F13 equals F23 because they're both k q squared over a squared. So when I look at this thing on the bottom, this is actually a 0 because I'm subtracting something from itself. Whereas at the top, this is actually just 2k q squared over a squared times cosine of theta. And so my answer is that the net force's x component is non-zero and positive, whereas the y component is 0. So if I go back here, which of my answer choices has a x component which is positive and a y component is 0? Well, positive x component means I point to the right, and a y component of 0 means I don't point up or down. So this guy that I circled is the answer because he's the one that points in that direction. Now you can kind of see that just from the vector addition, and if you're willing to not be completely perfectly justified, that's totally okay. Just simply notice that when I add these together, tail to tip, I'm going to get something roughly that points to the right. You see that? Let me use a different color. So I can follow F13 first, then I can follow F23 second, and then I get a resultant vector that points like this. And that resultant vector is the net force, and you can basically just kind of see the way it points, and that allows you to avoid all this messy algebra and symbols. But to fully justify it, you do need to do the math. But that's okay. I mean, this is a physics class, and I'm deliberately giving you a limited number of options. So it's totally okay to simply say, well, this is the closest thing based on some approximate reasoning, because often that approximate reasoning is more valuable than the symbolic reasoning.